All right, good morning. Welcome to the final day, day 3 of ISART 2024 in pursuit of consensus on clutter. Thank you for joining us, and we look forward to another great jam-packed day, but a little bit shorter day as we finish up this pursuit. And to lead us off this morning, we're going to get opening remarks from Charles Dietlein. He is from NTIA Institute for Telecommunication Sciences and a co-technical chair of ISART 2024. So welcome, Charles.
Good morning, everyone. As Jeremy said, welcome back to the third day of ISART. I hope you've all had a good few days. I know I have, but I've also lost my voice and I'm coming down with some sort of sinus thing, so please bear with me. So we've largely focused on the technical topic of ISART, that is clutter so far, but addressing the full theme of ISART, which is consensus, you see on the screen there, it's not just a technical matter, but a bigger picture endeavor that requires the expertise, not just technical expertise, and perspectives of everyone here. And because today is the last day, we need to think about the fact that it also requires a vision and a path forward. We can't just talk here and get on our airplanes and go back home and hope that we've made progress. Hope is not a plan. So today is not necessarily about advancing our technical understanding, although I'm sure that'll come up. It's really about building a stronger and more cohesive community, and this day is fully dedicated to that. So ideally, the outcome, which I just told Jeremy, since he's in charge here at the end, is that we can identify some specific steps that we can take to move forward. Now, I want to plant a few seeds of a theme that I hope will come up in the discussions today. I know it'll come up in the first technical talk and the second technical talk, but we'll see if it comes up again. Earlier this year, or maybe it was late last fall, John Chapin from NSF introduced us to the emerging topic of frictionless reproducibility. And in my opinion, one key aspect of building our propagation modeling and or spectrum management community is embracing this principle. And so what is it if you're not familiar? Frictionless reproducibility, which is a concept championed by David Donoho, a statistician from Stanford. If you don't know who he is, he's essentially, I think he's won what is the equivalent of the Nobel Prize in math. The concept emphasizes the importance of making research easily replicable without significant effort or obstacles. The concept is built on 3 pillars. Number 1, sharing data. Number 2, sharing code. And number 3, organizing challenges. The idea is that by ensuring that others can readily reproduce and verify someone else's results, we can enhance transparency, credibility, and the overall quality of our research, and importantly, the speed at which progress in research is made. So in this context, I want to highlight a few efforts in the RF community that have touched on those pillars, albeit they have little or nothing to do with clutter directly. The idea here is to think about where we've seen these pillars before and perhaps use them as inspiration for what we can do in this community. The first I wanted to mention is DARPA's Coliseum. So I'm sure a lot of you are aware of it, but it's a state-of-the-art closed-loop RF testbed that directly enables 2 pillars of frictionless reproducibility just by the nature of what it is. Coliseum provides a massive programmable RF emulation environment that can simulate real-world conditions, and it played a key role in DARPA's Spectrum Collaboration Challenge, demonstrating how challenges, one of those pillars, can drive innovation in spectrum sharing. Coliseum, which is now at Northeastern University, currently allows researchers or teams of researchers to test and develop new communications technologies and concepts in a controlled and repeatable setting. And that's due to having a shared code base that enables specific and detailed scenarios that different people can explore in that emulation environment. We've got the shared code base and challenges. Moving to the last pillar, or the third pillar of frictionless reproducibility, several efforts have been made to create shareable data sets in the RF community. One of those initiatives is NSF's RF Data Factory. No, this is just speech. This platform provides, so RF Data Factory provides well-documented RF data sets supporting research in wireless communication and spectrum sharing and management. By enabling access to these data sets, RF Data Factory enables researchers to validate their models and algorithms against each other, promoting transparency and, again, reproducibility. So having planted those seeds about efforts in the RF community that touch on these pillars, let's get back to today. So I want us to think about the diversity of perspectives here. We have researchers pushing the boundaries of models. We've got users applying these models to real-world scenarios. And we have policymakers guiding the frameworks within which we operate. All of these perspectives are important, and hopefully today we can combine our perspectives and thoughts into a vision of how we move forward together in this area in a way that benefits every stakeholder and participant. The sessions today are structured much like the last few days. I encourage active participation, as you all have. I realize it's the last day and we're all a little conferenced out here perhaps, but it's important to remember today especially, part of building a community is fostering an environment where every voice is heard. And so your technical expertise on the topic of clutter is actually less important today than it was the last few days. So if you haven't spoken up because of that, today's your opportunity. So to start the day off, we have a pre-recorded talk from David Donoho himself. He's probably flying over us right now from London to LA or San Francisco, so that's why he couldn't be with us. He's going to explain to us the principles and significance of frictionless reproducibility. Following that, Cobus Vandermeer will present a technical talk on the Powder platform, which is an NSF power test bed, and how it can be used in the context of frictionless reproducibility. After a break, we'll come back for a panel on openness, collaboration, and growing the community, moderated by Nick Lanneman. Following that panel, we'll break for lunch, and after lunch, Billy and Max are going to spend about 30 minutes hosting an open discussion and feedback session regarding Monday's tutorial, hopefully determining a path forward with code and data and perhaps challenges. So please come prepared with some thoughts to provide to Billy and Max after lunch. And I wanted to say that David Donoho's paper on frictionless reproducibility actually served as a bit of an inspiration for where we ended up with that tutorial, with Monday's tutorial. We had a lot of different ideas about what that should look like, and we ended up directly embracing two of the pillars of frictionless reproducibility. So after that, we'll conclude the day with a wrap-up panel with the panel's moderators, where we will synthesize the discussions and outline next steps. Before we get started, I want to thank Billy, Jeremy, Max, TPC, and the speakers and participants who've made this all possible. I know I've been in the back row this whole time. They've been doing the bulk of the work, and so I think it's been a great event, but mainly and only because of all of you. So enjoy the sessions, and I look forward to the discussions that'll take place today. Thank you. Sure, I'll just introduce Donoho's talk. Little background. We reached out to him. He was very engaged with us, over the calls and Teams meetings. He was in London for a conference this week, and he recorded a talk for us. There's a technical snafu in the video, which is that after the first slide, the slides are shown two to a screen side by side. So if you're in the back row or in the back half of the room, you might have a little difficulty making out what's on the slides. You don't want to move up, that's fine. Listen to the audio, it's very good, but I'm hoping we can get a revised version of these slides. He has a 1.5 hour talk on the same topic, so he's scrunched this down to 30 minutes for us. And he's aware of what we're doing in this community and that we want to try and adapt some of these principles, but he didn't have time. He's a very busy and famous person, didn't have time to incorporate a lot of the RF nature of some of the guidance we talked about in the phone calls. So I hope you appreciate the talk, and I know I did when I watched it last night, so enjoy the talk.
Hi, this is David Donoho. I'm a professor at Stanford. I'm the author of Data Science at the Singularity, a paper which has recently been published in Harvard Data Science Review, and which you can consult along with a set of discussions by 16 different authors. In principle, it would take me more than an hour to go in detail through everything that's discussed in all of that material, and you're free to consult it, but here I only have 30 minutes. Today, everywhere we look, there's media coverage of AI, and there's a dominant narrative which goes like this. In the last 10 years or so, AI became better than humans at many tasks, playing games like Go and chess, image classification and recognition, natural language translation, protein structure prediction. Then in fall of 2022, ChatGPT dropped on the unprepared public. It gave them access to large language models, and suddenly they could answer questions from medical exams and law boards and so on with answers that would be adequate to show expertise. Immediately, there was a stock market reaction, a reaction by politicians who were concerned about what this meant for unemployment, and a reaction by business who started to make large investments in having enhanced AI potential. Part of the excitement about this is based on the graph you see on the right side of the screen, which indicates that in recent years, there's been a quickening or acceleration of the pace of AI development, such that things that used to take years and years to go from rudimentary efforts by research labs to finished products that are human performant now can make that transition in only months. The thought that this was going to replace humans with some sort of artificial intelligence led to a political focus, leading to congressional investigations and to political interventions by regulators. The media began to tell us that soon we would have robot masters. And despite all of this, which is surrounding us and we can't escape in our normal daily lives, I believe that this narrative is both sensationalist and misleading, and that there is something happening, but the narrative that we're marinated in fogs our vision of what has really happened and makes it difficult for us to see what's going to happen. My discussion is in a paper that you can find on arXiv, and as I've said, it has now appeared also in Harvard Data Science Review, which also has an explain it like I'm 5 years old at the beginning of the article in case you want to first just get your toes wet. In my opinion, something very profound has been happening, but it's the fulfillment of some long-term initiatives in data science that data scientists have wanted for decades and decades, and which finally just came to fruition just now. AI singularity hasn't happened yet, and that whole narrative is a misdirection. If we pay attention to what's really been happening, we will get actionable information that will lead us in a much more productive path. To understand what's really been happening, let me just remark that smartphones, although we rely on them and they've made their way into our daily lives, have a much more fundamental impact than we imagine. And one way to understand what's happened is to realize that over the last 10 years, we've completely flipped the information inequality that used to exist. Now, peasants in countries all around the world have smartphones and can get information that's useful to them in a way that wasn't possible 10 years ago. And they get much more information today than residents of advanced economies had available to them even 10 years ago. This is a civilizational achievement that required many trillions of dollars of capital investment, and which has been happening in plain sight in front of us, although many of us don't pay much attention to it. The first thing that had to be done in order to achieve the civilizational transformation was to create a whole new style of information technology that supported the smartphone. Under this new style, the smartphone would drive queries to servers many times per day, leading to billions, tens of billions, and trillions of queries per day over time as this whole transition has unfolded. These involved smartphones wherever they were on Earth, contacting data centers, which could be geographically quite remote, in some cases in polar regions, and in many cases involving new connections to those remote data centers, for example, through undersea cable, undersea fiber. So there are now data centers north of the Arctic Circle that were not there 15 years ago, with massive numbers of CPUs ready to process requests from all of those smartphones. So it's not out of consideration for a resident of Southern Asia to be hitting a server in Greenland in order to get a query answered, maybe many times a day. This was never possible 10 or 20 years ago. As part of this, the availability of services commercially and on demand and for bespoke purposes, not just for the original purposes of smartphones, came about. And it's a giant cash cow to a number of the hegemons, which has been reaching levels of unheard of profitability in the hundreds of billions of dollars per year, as our whole civilization has started to take advantage of this amazing new architecture of the cloud. So what's happened in this decade at the level of civilizational transformation was the creating of massive compute, the creating of massive communications, the spread of information to previously uninformed populace, and a fantastic impact on human behavior. Another part that's not adequately discussed is that in order for smartphones to have all of these things, the cloud services had to be available for frictionless access. Namely, it had to be that the person who was in Southern Asia trying to hit the server in Greenland didn't have to supply credentials, didn't have to be involved consciously in the action. It just happened. Now, against that reality of what has actually unfolded, there's a much fancier narrative about singularity, which predates that reality, did not predict that reality, and somehow has captured everyone's mind. In 2005, Ray Kurzweil published the book, The Singularity is Near, which contained a narrative saying that pretty soon an artificial intelligence was going to take over and completely change life on Earth in such a way that humanity would not recognize what's coming next, and that singularity would be happening around 2030 or 2040. Part of Kurzweil's argument was, look, biological and technological evolution has been happening faster and faster throughout human history. And so if you consider on a line events ranging from life, emergence of humanoids, emergence of language, emergence of cities, emergence of modern organized societies, emergence of computers, personal computers, then on a log scale, these things are happening in such a way that change is coming faster and faster over time. And so we must be approaching some kind of vanishing point where things are happening so fast that it's all over in the blink of an eye. And part of his argument for how the last event on his timeline, emergence of computing, was going to drive this complete transformation of life on Earth is that computation is happening faster, as you can see in the left slide. On the right slide, his argument was soon, this is from a 2005 perspective, computation would approach what you could compute for $1,000 would approach what a mouse could do. And then some years after that, it would approach what one human brain could do. And then some years after that, it would approach what all human brains could do. But notice his scaling argument was based on Moore's law, which did hold up until the time that he was writing his book, but has failed spectacularly since. So his proclaimed reason that all these things would happen actually was not predictive. Nevertheless, what was predictive is that we would be approaching some kind of amazing scaling of computing in the coming years. It just came by different methods, such as GPUs, such as multi-core, that did not exist in his considerations at the time. So we go back to the points I want to make in this talk. The AI singularity is something that's very persuasive, that journalists love, intellectuals love, but it's a misdirection. Something did just happen, and it was very profound, but it's not the AI singularity yet. Instead, it's a different kind of development, as 3 long-term initiatives in data science came to fruition. These different developments can be enumerated as follows. First of all, in the decade of the 2010s, we achieved datafication of pretty much everything and initiated data sharing. We started code sharing of pretty much all kinds of code, and in such a way that it was very easy for people to re-execute. And then finally, we started creating globalized challenges where people all around the world could match wits with computational challenges and data and code supplied to them, and they could build on the baseline supply to make improvements. Because of what was happening in information technology, these things not only got achieved during the 2010 decade, but they were implemented as frictionless services so that you could gather data without doing anything consciously. You just embedded programmatically a line or two in your code. You could access code and re-execute it programmatically with no emotional involvement, no pointing and clicking, no paying attention to anything. And you could compete and challenge problems and submit your answers frictionlessly, and the leaderboard would update frictionlessly. All 3 of these particular achievements of that decade had been many decades in the building, but the particular achievement of that decade was to make them happen and make them happen frictionlessly. As we'll see, they were true revolutions. Datafication, just as an emblem of that, realized that in 2013, the Oxford English Dictionary word of the year was selfie. And in that same year, humans uploaded to servers 1 trillion images. These went into the servers of Facebook and Apple and Google, and they began humans to spend amazing amounts of time just looking at the images that they had uploaded and that other people were sharing with social media platforms. In a scientific setting, we started to have data sharing institutionalized such that you could now you could make journal publications that were just sharing data sets. For example, the Nature family of publications has the journal Scientific Data. Code and model sharing, for example, by GitHub, for example, using PyTorch, for example, using Hugging Face, came in during this decade, and it became very, very easy to obtain someone's model, to obtain someone's underlying algorithm, and in a live fashion, access it and re-execute almost unconsciously. Just ask for it to happen. You don't have to do anything special. No care and feeding. Then finally, the challenge problem paradigm came together, creating massive communities of people working to solve challenges jointly. An emblem of this is the fact that Kaggle made it to 1 million registered users sometime in 2017. So these are the three core data science trends that came to fulfillment. And I've claimed that these were a long time in developing, but they came together after the smartphone changed information technology to be this always on, 24/7, frictionless, universal product and service. We can understand that data sharing has been around a long time, since the earliest efforts at scientific publication in the 17th century. And we can look at how data sharing has changed over the years. In 1985, one could publish a book called Data with a CD-ROM in it. In 1987, an FTP site was initiated at UC Irvine to share data used in a journal called Machine Learning. And then data sets began to be important in the 90s and aughts, such as MNIST, CFAR, the Caltech pedestrian data set. And you today have frictionless data access through PyTorch or through OpenML that just require a string naming the data set you want, and then we'll just go out on the network and do the extract, transform, and load for you. OpenML is featured in these two slides. You can go to the website and see all the data sets that they have. They call themselves a worldwide machine learning hub. And with just a few lines of code, you can access any of the data sets they have. Just embed the access right directly into your Python script. Reproducibility and code sharing has been pursued for decades. And I, along with my co-authors, made an article about this already 15 years ago, in which we said we've been working reproducibly for 15 years. And it will take some time more, but we're getting there, and it's going to be transformative to science. Challenge problems have been in the works for decades. Most people know the Netflix challenge, or maybe the ImageNet challenge, which have been so important in machine learning. But that whole trend started years and years before. And you can get the full story if you go to a talk given by Mark Lieberman at the Simons Foundation, indicated in the right-hand slide. Challenge problems over time have shown that year after year, challenge performance improves. And in fact, in an important effort, face recognition studies by Jonathan Phillips has shown that the ID verification error rate over time in a variety of DoD and NIST organized challenges has gone according to a Moore's law, doubling in accuracy every couple of years. So we had been working on data sharing, we had been working on code sharing, we had been working on challenges to come up with better algorithms, But suddenly these were brought together as frictionless services, single click access, single line of code access in the 2010s. That allows frictionless replication of any result that's being worked out under this frictionless reproducibility standard. And then what you have within a group of people who are working frictionlessly is a frictionless research exchange, such as Hugging Face, where people share their models as they evolve, and you can always find the latest and greatest of any model for any of the basic leaderboards that are out there. My claim is that when you bring all of these together and you have a frictionless research exchange, then you certainly have singularity. And how we can see this is in the rapid spread of innovations where the innovation has been properly published under the frictionless reproducibility standards that I've just described. Someone has shared the data, they've shared the code, they've demonstrated that on a benchmark challenge, the code works well. As soon as you do that, you open yourself up to a global audience who will work to use, spread, and improve what you've done. And you can see this in many, many ways. But for example, in improvements in machine learning, such as the spread of deep learning, the spread of transformers, and there are many pieces of evidence downstream of what I'm telling you that you can witness. Scikit-learn, which is something that's part of this frictionless reproducibility rubric that I'm talking about, gets something like 1.5 million downloads every single day. At the same time, what happens because working frictionlessly makes people want to use certain kinds of code is that if the code is written to a standard that it assumes certain hardware, then that hardware automatically becomes something that everyone wants, because in reality, they want to work reproducibly, but what that requires is that they have the same hardware as whatever was used in the system that they're reproducing. The result of that is that NVIDIA H100 GPUs became among the most coveted objects on the planet. Now, I've claimed that the particular components of this frictionless reproducibility paradigm are true revolutions. And in the written version of my talk, you can see that it's revolutionary in two ways. First of all, philosophical, because anything that's published by these standards, someone else can point and click and check that they get the same answer on the same data set. Secondly, it's scientifically revolutionary because a lot of the work in scientific publication was really around enabling reproducibility. But if you've reproduced it using these standards, then you've taken away a lot of the need for reporting in the original scientific publication. It's possible to have much shorter papers and yet communicate much more accurately what you've done and what contribution you've made. As a result, there's a new publication standard which is being used, for example, in CS and empirical machine learning conferences, where you have 8-page papers. Page 7 always has a table of the results. There's always a supplement describing the code and data. And this became so stereotyped that I'm sure there'll be large language models authoring in such a way as to produce these reports for you soon. So we've got true revolutions happening. It's all part of this new paradigm, which is creating a kind of singularity in the productivity of research. And there'll be a true before and after period. and there's really no going back on any of these things. Now, if you onboard some of what I've said, then you can ask, well, what should you do? One thing you can do is to credit this new worldview as being a real thing and as being something that's driving the changes under empirical machine learning and the AI revolution that you see. You can also credit the idea of challenges distributed globally and so on as driving a lot of the progress that you see in AI and in the associated machine learning software. Once you credit those, you'll immediately see that you should be doing relevant research by adopting this paradigm and working reproducibly. So these are prescriptions for you, and there's a lot more discussion of this in the HDSR article that I've mentioned. In conclusion, today's AI singularity is a media darling. It's an obsession in some ways, but it oversells an admittedly charismatic notion, the AGI singularity. Now, the acceleration that we're seeing is real, but it's not an AI only acceleration. In fact, it's more broad, and it's due to the advent of frictionless services. In the particular case of data science, those frictionless services give us a new frictionless reproducibility paradigm where we get the data with no effort, we get the code with no effort, we can participate in challenges with no effort, we can enter our improved results with no effort. When all of these come together, we have a frictionless research exchange where people are sharing code, data, and results frictionlessly, and then we have a singularity, which is the reproducibility singularity. On the other side of singularity, there'll be many interesting happenings. There's discussions of this in the HDSR article. I welcome you to go look at that. I believe that if you onboard what I'm saying, you'll see that there's a great deal of leverage available to you by making your projects work reproducibly under this frictionless reproducibility paradigm. Adopt this way of working, become part of a frictionless reproducibility exchange. The community that you belong to will make fantastic progress quickly, as we've been seeing in field after field where the progress of AI has been recorded. It's all been frictionless reproducibility exchanges of people working in this fashion. Thank you so much for giving me the opportunity to speak to you today. And I wish I could be there. I hope you'll have a chance to take a look at the article, and good luck on the success of your conference. Thank you.